Hello friends, let's start today's lecture. We finished today the topic of joint distribution with the third part. In the beginning, let us recap the previous material, what we have covered, and let's extend this to the general case of n variables, because in the previous two lectures we spoke mostly about two random variables. So let's try to extend this to the general case. So we started with the definition of a random vector, and the random vector is just an ordered vector of random variables. So it might be 2, it might be 3, 4, 5, and so on. When we use the matrix notation or vector notation, we usually use the bold letters here. So whenever you see the bold X, it means that it is a vector containing several random variables. We know that for random vectors, we can introduce joint probability functions. For the discrete random variables, we introduce the joint probability mass function, which simply means the probability that each variable equals to some particular value. x1 equals to the small x1, x2 equals to the small x2, and so on, up to xn. When we talk about the continuous random variable, we introduce the joint probability density function. This density function does not have the same meaning as the previous one, and the density function is defined with the help of the conditional distribution, cumulative distribution function. So the cumulative distribution function is defined as the capital F of several random variables, which simply means that this is the probability that jointly or simultaneously all of these random variables from x1 to xn are less than or equal to some particular number. And then when we integrate this joint PDF over the range of values from minus infinity to small x1, small x2, small x3, and so on, we get this cumulative distribution function for the continuous random variable. So I hope you remember the connection between these two. This is the derivative of the cumulative distribution function. Cumulative distribution function is the integral of density function. Then, with the help of joint distribution functions, we can introduce the marginal probability functions. So basically, marginal probability functions are the univariate cases derived from the joint probability. These marginal probability functions are the same probability functions as we used before we introduced the joint distributions. So these are probability functions for only one random variable taken from this vector. So for the probability mass function, when x is discrete, we define this marginal probability function as the summation of joint probability mass function over all other random variable values. So all x2, all x3, all x4, and so on till all xn for the first random variable. So that's how we define the marginal PMF, and I hope you remember the examples that we used. For the marginal probability density function, we do the same, but instead of summations, we have integrals from minus infinity to plus infinity, or from the lower border to the upper border over all variables but x1. So x2, x3, up to xn. So once again, this is the repetition, nothing new here. I just extended this to the multivariate case, not 2, but n variables. So then, with the help of joint distribution functions and with the help of marginal probability functions, we can find, or we can define the conditional probability functions. So the conditional probability mass function in the case if x is discrete is the following. So this is the probability mass function for variables from x2 to xn when x1 is known. When I know the value of x1, I want to calculate the probability for all other variables being equal to x2, x3, and so on. And that's simply the application of the conditional probability definition that we know from lecture number 4, I suppose. And this is the fraction of general probability mass function, joint probability mass function for all variables, and the marginal probability for x1. And for conditional PDF, the logic is the same. We just use the density functions here. Yeah, so we can introduce the idea of independency, and if you remember, the idea of independency was introduced for 2 variables. It was in the last lecture. So now when we have more than 2 variables, we can introduce the independence to 2 notions of independency. So there is a mutual independence and pairwise independence. So mutual independence means that for discrete case, the probability mass function, joint probability mass function, equals to the product of marginal probabilities. So I just extended this definition of independence for 2 variables. I extended this case to the n variables. That's it. But look, pairwise independence means that I am able to calculate these joint densities only for 2 variables. So this is something like a marginal density, but for 2 variables. And this must be equal to the product of their individual marginals. So the mutual independence assumes the pairwise independence, but not the reverse. So if we have, let's say, 3 variables, first and second might be pairwise independent, but first, second, and third are not mutually independent together. So sometimes it happens. I hope you understand this logic. And for the continuous case, we apply the same idea, but based on the density functions. Then, with the help of probability functions, we defined the expected values. And we have said that there are 2 approaches in order to calculate the expected values. So one approach that you can calculate expected values using joint probability functions. So for, let's say, variable x1, the expectation is the sum of this product x1, so all values of x1 multiplied by the joint probability function. So now the summation occurs over all variables, all x1, all x2, all x3, up to xn. For the continuous case, we integrate over the whole range of variables from x1 to xn of this product x1 multiplied by the joint density function. So here is the 3. But now look, if we extract this sum, if we take this sum over x1s out of the summation sign, we can get inside the marginal probability function, the marginal probability function for x1. So try to see the similarity here. When I calculate the marginal probability function for x1, I sum this joint probability mass function over all variables starting from x2. So all x2, all x3, up to xn. So now, once again, if I take this x1 and summation over x1 out of all other sums, if I will factor out, I will get this. I will get that inside I have the probability, marginal probability mass function for x1, and this is simply a univariate case of calculation of expectation. So this is what we know from lecture number 7, I suppose, when we multiplied x1 by the probability mass function. So both approaches give you the same result, whichever is more suitable, you can use it. And for the continuous case as well, we can, when we integrate over all variables but x1, we will get this. We will get the marginal probability density function. And when I have this last integral over x1, it exactly defines me the expectation of x1 using the marginal probability function. So both ways are possible, whichever you prefer. So the same holds for any function of these random variables, which is also a random variable. And the same approach for calculating the expectation holds for this. So I just plug, instead of x1, I plug this function, g of x1, x2, and so on. But of course, if you use this, I need to use the general case using joint probability functions, not marginals. Because if it's a function of several variables, definitely I need to use the joint probabilities. So the last thing we introduced in the last lecture was the covariance and correlation. So we are able, this is not possible to extend to the case of several random variables, because covariance and correlation, they are defined only for the pairs of random variables, only for 2 random variables. So the covariance is defined as the expectation of the following expression. So the product of deviations of the random variables from their expectations. And the correlation is defined as the fraction of covariance and the product of standard deviations. Now, what can we do if we have several random variables? So when a random variable, when a random vector has more than 2 random variables, we introduce the variance, covariance, and correlation matrices. So there are going to be matrices. One is defined as this bold sigma, and another one is usually denoted as bold rho. So how does this look? So the variance covariance matrix looks like this. So sigma 1, 1 is simply the variance of the first variable, sigma 2, 2 is the variance of the second variable, sigma n, n is the variance of the nth variable. And on the so out of the main diagonal, sigma 1 1 is the covariance of first and second variable, sigma yn is the covariance of first and nth variable. And the same here, so the covariance of second and 1, which is the same as 1 and 2, so these two numbers must be equal, these two numbers. Sigma n1 is the same as sigma 1n, so we have a symmetric matrix, and this is going to be also squared matrix because we have n rows and columns. So that's how we usually work with the random vector of 3 or more variables. We don't have only one covariance, we have 2 or more covariances. And the same for the correlation, except for this, because on the main diagonal we have ones. I forgot to put 1 here. We have ones because the correlation of the variable with itself is 1. And out of the main diagonal we have the correlation coefficients pairwise. First, second variables, first, third variables, and so on. Yeah, we introduced the new mathematical concept. I mean, we never used matrices up to this moment. Of course, I hope that you are familiar to matrices. But now I think that we are gonna use matrices oftenly from this moment. So yes, here is the explanation. So sigma ii is the variance of variable xi, sigma ij is the covariance of xij, and rho ij is the correlation coefficient of variables xi and xj. So this is the brief recap of what we used before, of what we already know, and a small extension to the case of several random variables, more than 2 random variables. Let me know if you have any questions. Let me know if you don't understand something from this. So that's the overall picture of what we already know about the joint probability distributions. Is everything clear about it? I've heard that you are very active on the exercise sessions and you solve the problems kind of easily, so I think that no issues here. Okay. I don't know what silence means. Either you are so overwhelmed with this material and you even don't know what to ask, or there are really no questions. So now let's move one step more and let's discuss how we can calculate the expectation and variance of linear functions of random variables. So suppose we have 2 random vectors. One random vector of n variables x, and another random vector is the vector of variables y from 1 to m. For each of these random variables individually we have the expectations, so we denote expectations of x with the letter mu I for each of these random variables, and we denote the expectations of variables y with this he j. Let us define the linear functions of these 2 random vectors. So one is gonna be u1 and this is just a linear combination of random variables x multiplied by some constant a. So we take random variable x1, multiply this by some coefficient a1, plus random variable x2 multiplied by some coefficient a2, and so on up to n. And the same story for the random variables y. We take y1 multiplied by b1 plus y2 multiplied by b2 and so on. And these two are defined as u1 and u2. So now the question is, what is the expectation of each of these combinations and what is the variance of each of these combinations? So those are constants. The following holds. So first of all, the expectation of u1, the same for u2, is simply the sum of these products. So we multiply ai by mu I and then sum over them. This is simple, and this comes, let me show you. We know this property. This property has been defined. Where it was defined? Yeah, this property was defined here, if you remember. When we find the expectation of the sum, we simply break this down into the sum of expectations. And that's exactly the property that we use in order to get this. Because if we calculate the expectation of this sum, we break this down into the sum of expectations of a and x. And then I can apply the property number 2, take out each coefficient of the expectation sign, and then it's going to be a1 expectation x1, a2 expectation x2, and so on. And finally, we have this. So I kind of omit the proofs of these. They are more or less must be clear based on this. So the second is the variance of this linear combination, and that's where we need variance. So basically, yeah, we didn't tell it. Let me check. Did we tell about this in the last lecture? I guess no. Yeah, we didn't tell about it. Yeah, that's exactly where we introduced this thing. So look, regarding the variance of u1, let me remind you one thing. I guess we spoke about it at some point of time. Yeah, when we spoke about variance, I guess it must be somewhere here. Yeah, look. So here I noted that generally variance of x plus y is not equal to variance of x plus variance of y. So this holds for expectation. Expectation of x plus y equals to the expectation of x plus expectation of y. But it doesn't hold in general for the variance. And that's, so it was in the lecture number 7. So now in lecture number 11, we exactly can see what is the right way to calculate the variance of this sum, but actually it's in general for n variables. So we, first of all, we have this term, which is kind of logical. So we take the coefficient squared multiplied by the variance of each random variable, and then we sum over them. But also we have this additional term, and this looks ugly. So the double summation of something, but let's try to understand what happens here. And then we will see the example how to work with that. So I'm taking coefficient AI, I'm taking coefficient AJ, so from these coefficients, multiplied by the covariance of between the respective variables, so xi and xj. So basically this is the coefficient in front of xi, this is the coefficient in front of xj, and then I multiply these two coefficients and I take the covariance, multiply the covariance by this. And look, I sum over all these terms for the values of I that do not exceed j. Look, why do I do this? Because here I does not exceed j in this case. So sigma 1, 2, sigma yn, sigma 2n, and so on. So here I exceeds j. So sigma 2, 1 is not in that sum. So sigma 2, 1 is not counted. But as I know that these two sigmas, they are equal, I simply multiply by 2 here. So I know that covariance of ij equals to the covariance of xj, xi, and therefore I don't need to calculate that another covariance, I simply multiply by 2. So that's what I do. Basically, I take only the covariances above the main diagonal, only this triangle here in the covariance matrix. Only this triangle is counted. And the lower triangle is not, because the values there are exactly equal to the values of the upper triangle. And that's how the variance of this linear combination is calculated. So that's why we really need these covariances. And finally, the covariance between these two linear combinations is the double summation for all covariances between all variables xi and all variables yj included into these sums, multiplied by the respective weights. So we don't have any variance here, so only this, which is more or less simple because now we need to calculate the mutual covariances of all x1 and y1, x1 and y2, x1 and y3, and so on, depending on how many y's do we have here, then x2, y1, x2, y2, and so on. So these pairwise covariances, then we calculate them, then we multiply them by the respective coefficients, and then we just sum over all i's and all j's. So the most important thing is here, which has a very important practical application, for example, in finance. And that's what I will show you. Just recently, yesterday, in the course of Applied Corporate Finance, we analyzed with students 3 stocks. So stocks of Adidas, BMW, and SAP. SAP is the German software producer. So suppose that we have 3 variables, R ADS, R BMW, and R SAP, which are the daily stock returns of these 3 companies. So these 3 are random variables. We don't know what's going to be the return, let's say, in the next day, today. Suppose the following. Suppose that we know that the expected daily return for Adidas is 55,000%, and shouldn't be Amazon, sorry, it should be Adidas. And the standard deviation of this return is 1.908%. So these numbers are calculated from the real data, I suppose from 2010. Yeah, so for BMW, we have the expected daily return 3.1 thousandths percent, and standard deviation is 0.68. And for SAP, we have this expected return and expected standard deviation, the standard deviation of the return. So, as I said, we treat these three returns as random variables. We have these parameters for the random variables, and then we need to calculate the covariances between these returns. So the covariance of the returns of Adidas and BMW is given with this number. The covariance between the return of Adidas and SAP is given with this number, and the covariance of BMW and SAP, so pairwise covariances, right, is given by this. So basically, we can calculate also, let me show you, we can calculate the correlation coefficients simply from here. I need to take the covariance 0.30175 and divide this by the product of variances. So for example, the product of standard deviations here. So I divide this by 0.01908, and then I divide this by 0.02068. So the correlation coefficient between Adidas and BMW is 0.44. And as you remember, the correlation coefficient measures the strength of the linear dependency, which is from -1 to 1. So it's not that strong, but still positive relationship, which means that whenever the stock return of Adidas increases, then the stock return of BMW also increases on average, but the relationship is not as strong, as I said. So we can do the same for any other pair of stocks in order to calculate how tight their daily returns are connected. So suppose that we invest our money in the following proportions. We invest 30% of our capital into Adidas, we invest 50% of our capital into BMW, and we invest 20% of our capital in SAP. So now let's go back to that general formula that we used. So what do we have? We have three random variables, which are stock returns. We have coefficients, which are the portfolio weights. And we have the characteristics of these random variables, which are expectations, variances, and covariances of these returns. So now the question is, what is going to be the expected return and variance of the portfolio? So given all this information, given all this data. So in order to calculate the expected return, we just need to calculate the weighted average of these three returns according to their weights, which is simple, right? So I take the weight of Adidas, multiply by the expected return of Adidas. I take the weight of BMW, multiply by the expected return of BMW. I take the weight of SAP and multiply by the expected return of SAP. And here is my expected return, daily return of my portfolio. So it's 0.0373%. So basically, if you think that this is the small number, when I multiply by the year return, it's going to be something like 13.6, which is more or less nice for the European market. Now, regarding the variance of the portfolio return. For the variance, we need to do this operation here. I need to take the square of each weight, multiply by the variance of each return, and then I need to add these twice these expressions. So the first line here, I take the weights squared here, here, and here. And since I'm given the standard deviations here, I need to square them in order to find the variances. So here the variance of Adidas, here is the variance of BMW, here is the variance of SAP. So that's the first step. So now I need to calculate that sum from here, this sum. And this is just a pairwise multiplication of covariances by the respective weights and the coefficient 2, which is here. So 2 times weight of Adidas times weight of BMW times the covariance between Adidas and BMW. Plus 2 times weight of Adidas times weight of SAP times the covariance between Adidas and SAP. Plus 2 times the weight of BMW, weight of SAP times the covariance of SAP. So finally, the variance of portfolio is here. So now, when I take the square root of this variance of the portfolio, I get this 1.2643. And then this is the illustration. You have probably heard about the idea of diversification. Don't put all your money into one stock. Try to diversify. If you are buying stocks, try to buy different stocks, which have not perfect correlation of their returns. And that's exactly the numerical illustration of this principle. Because let's compare this standard deviation, which is the measure of variability of your future return, so measure of uncertainty, let's say. Let's compare this with the uncertainty regarding each individual stock. Look, the uncertainty about Adidas is 1.9, which is the lowest out of all the other stocks. But combining your stocks in the portfolio, you significantly reduce this uncertainty because the standard deviation now is much, much lower than any of the individual stocks. Yes, your return is also kind of lower, but your return is above these two stocks, while your risk is much lower. So the standard deviation of a portfolio is much less than any of the individual stock, and this is the illustration of the diversification principle. So that's how in practice we use this idea of covariance and correlation. This is one, let's say, the most popular and the most famous example of using correlation. Of course, there are much more other examples. Maybe some of them are technical examples, but this is the most practical one. Any questions about it?
No question.
As you can see, the most problematic part comes here. Because, okay, we have 3 stocks, which is more or less nice. Suppose that we have 4 stocks. So if we have 4 stocks, how many covariance do we have? We have pairwise covariances of 4, like, okay, so like 4 with 3 others, so we have 3, we have 2, we have 1, we have 6 covariances, right? If there are 4 stocks. If there are 5 stocks, we have 4, 3, 2, 1, which is already 7, 9, 10, which is already 10. So the number of covariances as the number of stocks increases, the number of covariances increases very fast. And it's kind of not very nice to calculate all the sums all the time. And that's where the matrix notation can help. If you remember how we work with matrices, and especially when you know how to work with matrices in some software, so the matrix notation helps a lot. Look, if we define the vector of weights as this, 0.3, 0.5, 0.2, so those are our investments into the stocks. And this means that we are talking about the column vector, right? So I just write it like this to save the space, not to put just a column on the slide. Sorry. So define the vector of returns here. Once again, this is the column vector given this transpose sign. So here is the variance covariance matrix. So I grouped all the data about standard deviations and covariances into the matrix. Look, on the main diagonal I have variances, so this standard deviation squared, and on the over the diagonal I have the covariances. So now, the expected return of my portfolio is simply the product of the transpose vector of weights, row vector, and the column vector of the expected returns. Which, if you remember how we multiply matrices, is just 0.3 multiplied by this, plus 0.5 multiplied by this, plus 0.2 multiplied by this. That's simple. When I want to calculate the variance of a portfolio, it looks like the following product of matrices. So it's a row vector of weights multiplied by the variance covariance matrix multiplied by the column vector of weights. Look, 0.3 multiplied by this, 0.5 multiplied by this, 0.2 multiplied by this. So after the multiplication, and then I sum over them. Then I have the same 0.3 multiplied by this, 0.5 multiplied by this, and so on. So after the multiplication of this and this, I have what? I have the, wait a second. Should be, yeah, it should be a row vector. Should be a row vector, 3 by 1. And then look, 0.3 times this gives me exactly the first term, squared weight multiplied by the variance. Then 0.5 multiplied by this gives me the first term, which is the weight of BMW times the weight of Adidas times the covariance between Adidas and BMW. Then 0.2 multiplied by this gives me the covariance of Adidas and SAP multiplied by the weight of SAP multiplied by weight of Adidas. So basically this is the same. I mean, all the operations of the multiplications and summations are going to be exactly the same. The only difference is that if you are using software, it is much simpler than kind of the handwritten calculation that we did here. And of course, extending these matrices to 4 by 4, 5 by 5, and so on, it makes our life much simpler. That's some additional, let's say, illustration how we can use this linear algebra in order to simplify our life and in order to make our calculations faster. So this is somehow out of the scope of this course, so I'm not kind of go deep into details. Just wanted to show you that we also can apply something interesting here. Okay, so now we know the two concepts for now. We know the concept of independence and we know the concept of covariance. So very important thing that you don't need to mess these two concepts together. So they are completely different. So if you remember, we started in the recap, we started with the idea of independence, that two independent random variables are those variables for which the joint distribution function equals to the product of marginal distribution functions. And of course, if we have two independent random variables, and if we have some functions of these independent random variables, then the expectation of their functions equals to the product. The expectation of the product of these two functions equals to the product of the expectations of these two functions. I guess we had it. We had it here. No, we didn't define the what was it here? Yeah, it was here. Yeah, we introduced this idea that the expectation of a product equals to the product of expectations only when the variables x1 and x2 are independent. So look what happens. If in this case a covariance between these two variables is 0, which means that independent random variables are not correlated or uncorrelated always. It always holds. But the reverse is not true, which is important, and don't mess things up. If covariance is 0, it does not mean that two random variables are independent. They do not have linear correlation between them. They do not have linear dependency, but probably they have non-linear dependency, which is quite important. So let me briefly illustrate you this idea with a simple example. So I didn't put it here, but actually it's quite easy to show how it works. So let's define variable x, and the variable x has values of, let's say, -3, -2, -1, 0, 1, 2, 3. And let's define variable y, which is simply the square root of the variable x. And let's say that the probabilities, the marginal probabilities of them are equal. Okay, so it's gonna be something like here we have x, here we have y. So we have 0, 1, 4, 9. Here we have -3, -2, -1, 0, 1, 2, 3 here. And then what are gonna be the probabilities? It's for 0 and 0. We have, how many combinations do we have? Um, 1, 2, 3, 4, 5, 6, 7. 7 by 3, it's 21. 21 by plus 7, 28, right? So it's going to be 1 over 28. for each of these combinations, and here it's gonna be 2/28. Yes, the sum must be equal to 1, so let's check that's true or not. Oh no, 175. Yeah, so they must be equal for all. Yeah, so now it's correct. So we have the joint distribution function for the discrete random variables x and y, where this is the x, this is y. And basically we have marginals, so the marginals, so here is the marginal of x equals small x, which is just the sum of these probabilities, and here is the sum, this is the of y equals y, is the sum of these. And so finally I have, wait, this is strange, it shouldn't be equal, right? So I have 0 in less cases than I have 1. So, here, 4 here. So we have this joint probability distribution of these two variables with the following marginals. And now look, if I want to calculate the expected value of x, this gives me the following. So I need to multiply all possible values of x by the respective marginals. So basically I do this very fast with the help of Excel function sum product. So here and here, and that's gonna be 0 basically, right? So it must be 0. So now the expectation of y is what? So this is the sum product of the values of y, which are just 4 values, and the respective probabilities. So the expectation of y is number 4. Must be right, exactly 4. So now what is gonna be the expectation of x multiplied by y? Just in order to calculate the covariance, we need to know this. So wait a second, how should I calculate it? I need to, so I have only 7 values here. So let's say x equals x and y equals y. If I do this in the following table, it gives me 1/7 everywhere, and then I simply multiply these things. So x, y, which is this multiplied by this, and then I take the respective probabilities. So this probability is multiplied by this here. Okay, you see that this is 0, almost 0. And now the covariance between x and y is what? So it's x multiplied by y, sorry, it's expectation of xy minus expectation of x multiplied by expectation of y. So the covariance is also 0, definitely. That's what I wanted to show you. But are these variables independent? So the question is, are x and y independent? So in order to check this independency, we need to take any pair of values. Let's say x equals -1, y equals 2, and we need to check if this is equal to the product of their marginals. So what is the probability that x is -1 and y is 2? So x is -1, y is 2. Sorry, y is 4. Y is 4. So it's 0, right? This is the probability. So it's 0, while the probability that x is -1 equals this 1/7, 0.4286, and the probability that y equals 4 is here, 0.2828,571. So definitely x and y are not independent. X and y are not independent. So that's an illustration. Look, we have not independent variables with the covariance 0, because I constructed these variables in a way that they are dependent. So y is just a square of x. So don't mess these things. Covariance shows you the linear dependency between two variables. When the dependency is not linear, like here, the quadratic, because as I said, y was the squared of x. If the dependency is quadratic, cubic, or some other nonlinear shape, the covariance might be very close to 0 in the correlation as well, while the variables are dependent. That's an important thing, and don't forget about it. So now we move to the I guess last thing in the topic of joint distributions is the conditional expectation. So we know conditional probability. So now we define the conditional expectation. This is the expectation. So okay, if you have two variables, x1 and x2, then the conditional expectation of any function of x1, not only x1, as I said, any function, given that x2 is equal to some number. So basically we know something about x2. We know how much is x2, what is the expectation of a function of x1 or just x1. This is the following thing. So as usual, when we calculate the expectation of some function, we take this function multiplied by the respective probability mass function, and now we have the conditional probability mass function of x1 given the value of x2. If these two variables are discrete, as you may guess, if these two variables are continuous, then we substitute the summation with the integral and put here dx. So this is called the conditional expectation. The conditional expectations play a very important role in statistics and econometrics. Why? Let's see the example. Given the value of one variable that I know, given x2, for example, price discount or cigarette tax increase or additional year of education, what is the expected value of the other variable? For example, increase in sales. So if I want to impose 20% discount, how much increase in sales I can expect? If the government imposes additional tax on cigarettes, what is the expected number of reduction in what is the expected reduction in the number of smokers? If I study one more year in the university, what is my expected additional salary? Those are the questions that we are gonna investigate. I mean, not exactly these questions, but the types of questions during the econometrics course. And as you may guess, this is the cornerstone of all the data analysis. So we are looking for some dependencies or connections between different variables, and we are, what is most important, we are trying to answer some questions. What if I change this? What do I expect in the outcome variable? That's the most interesting thing. So we don't want just to find some connections between the processes. We want to use these connections in order to make some decisions, of course. So that's why we are interested in the conditional expectation as well. So now let's see how we can calculate these conditional expectations based on the data. So you see the familiar example of the discrete random variables distribution with joint distribution and marginals here. What if you want to calculate the expected value of x1 given x2 is 0? So if you remember the setting, this is what? x1 is the number of clients standing at the first counter in the supermarket, and x2 is the number of clients standing at the second counter in the supermarket. So overall we have 3 counters and we have 2 people in the supermarket. So now, how many clients do I expect at the counter 1 if I see that there is no person at the counter 2? That's a question, precisely the question that we want to answer. So first of all, we need to calculate the conditional distribution of x1 given x2 is 0. So the probability that x1 is 0 given that x2 is 0 is 1 over 9 joint probability divided by 4 over 9 conditional probability. The probability that x1 is 1 given x2 is 0 is 2 over 9 over 4 over 9 is 1/2. And the probability of x1 is 2 given the x2 is 0, it's 1 over 9 divided by 4 over 9 here. So when I have these probabilities now and I have the values of x1, 0, 1 and 2, I can calculate the expected value of x1 given x2 is 0, which is simply 0 times 1 over 4 plus 1 times 1 over 2 plus 2 times 1 over 4, which is 1. 1/2 here and 1/2 here. So if I see that there are no people at the second counter, I expect 1 client at the first counter, which is reasonable because if there are 3 counters, there are no people at the first counter, then I believe that 1 person is standing at the first counter and 1 person stands at the third counter. And for the continuous random variables, if we have the following density function, I took this from the example in the lecture number 9, where we exactly calculated these conditionals. So it was here about soft drink machine. X2 was the amount of supply at the beginning of a day, and x1 was the number of sales during a day. And then we had this joint density function, and we know this conditional density f of x1 given x2, which is what? Which is the density of the sales given some supply in the beginning of the day. If I know how much do I have in my soft drink machine in the beginning of the day, I build the density function for the volume of sales. And that was the density function that we derived in the lecture number 9. It's here, 1 over x2. So you see that this is the function of x2. So now, what is the expected volume of sales given x2 is some particular value, and then given that x2 is 1.5. So in general, the expected value of x1 given x2 we simply take the integral of x1 multiplied by the conditional density function here, integrated from 0 to x2. Why? Because x1 is bounded between 0 and x2. Don't forget about this. So first step here, I take 1 over x2 out of the integral because this is treated as constant. And the integral of x1 is x1 squared over 2, evaluated between these 2 points. So I plug x2 at the place of x1, and x2 squared over x2 gives me just x2 over 2. So this is the conditional expectation of x1 given the value of x2. So give me x2 and I will tell you that the expected volume of sales is just a half of my initial supply at the soft drink machine here. And for example, if I have x2 equals 1.5, the expectation is 3 over 4. 1.5 divided by 2. So we are gonna work with these objects, with the conditional expectations, every week during the econometrics course, because we are gonna build these objects based on the data. As I said, tell me the price discount and I will tell you what is the expected volume of sales. Tell me the cigarette tax and I will tell you how many smokers is there. Tell me the number of education that the person has and I will tell you what is the average salary of this person. Of course, we are talking about expectations, and these expectations are the characteristics of random variables. Of course, you are never able to say the precise value of this variable, but rather some, let's say, measure of central tendency. Questions about the expected values? Okay, so then if there is an expected value, there must be variance. So conditional variance is given as the following expression. If we want to calculate what is the variance of x1 given a particular value of x2, we simply calculate this as the expectation of x1 squared given x2 equals x2, not the square bracket here, minus the expectation, conditional expectation squared. So this must be the familiar formula of variance that we used from the lecture number 7. Yeah, here. But now instead of just total expectation, we are using the conditional expectation here. Again, an example. If you want to calculate the variance of x1, given that x2 is 0, how should we do this? We know the expectation, which is 1. What is the conditional variance? First of all, we need to calculate the conditional expectation of x1 squared, given x2 is 0, which is the same expression as we used, but instead of x1, I taken x1 squared, 0 squared, 1 squared, 2 squared. And this is, I suppose, 3 over 2. So let me check. 1/2. Here I have 1. 1/2 plus 1 is 3 over 2. Yes. So now conditional variance is 3 over 2 minus 1 squared, the expectation, the conditional expectation from the previous slide. And this is 1 over 2. So the variance of x1 when I know that I'm in the first column here. I know exactly where I am, is 1/2. So applied to the continuous random variables, so the major difficulty is just taking integrals. So since we know that the conditional density function is 1/x, and we want to find the variance of x1 in general, and then the variance for the particular value of x2. So in general, first of all, we need to calculate this expectation of x1 squared, which is now I plug x squared here. Take 1/x out of the integral. Inside I have x1 cubed over 3 here. Then instead of x1 I plug x2, so minus 0, which is here. So x2 cubed over x is x squared over 3. So this is my expected value of x1 squared. Okay. Now variance is x2 squared over 3 minus x2 over 2 squared, the expectation from the previous example. And this gives me x squared minus x squared over 3 minus x squared over 2 over 4, sorry, which is 4x squared minus 3x squared over 12, and finally it's x. Oops, sorry, it must be x squared over 12. Yeah, there is a typo. Not x 2 over 12, but x squared over 12. Make note changes. Yeah. So finally, when we plug 1.5, this is also not the correct thing, right? Because it must be 1.5 squared divided by 12, which is 0.1875. So I guess it's 9/4. 4 times 12, 9/48, right? So it's going to be 9/48 here. Because of this calculation is also not correct. Okay, so finally, what do we see regarding the conditional expectation? So we see that the conditional expectation is the function of x2. So for example, when we talk about x1. Since this is a function of the random variable x2, we know that any function of a random variable is itself a random variable. And since this expectation is a random variable, because it depends on x2, it must also have a mean and a variance. So our last step in the joint distribution topic is going to be to understand what are the means and variances of these conditional expectations. So let's see. If you have x1 and x2, and if those are random variables, then the expected value of x1 equals to the expected value of x1 given x2. So basically, we need to reverse things, right? So the unconditional expectation of x1 equals to the expectation of the conditional expectation of x1. This is called the law of iterated expectations, or the law of total expectation, depending on the textbook that you use. So what is here? So here is the expectation of x1 given x2. So we use the conditional probability of x1 given x2. So the inside expectation is with respect to the conditional distribution of x1 given x2 here. And then look, when we have these conditional distribution and conditional expectation, the outside expectation is with respect to the distribution of x2, because now inside we have a function of x2, and dependent on the values of x2, we are taking the other expectation here. So you will see an example how exactly it works. And the variance of x1 equals to this. So this is the expectation of a conditional variance plus the variance of a conditional expectation. Kind of some mixture. This expression is also used oftenly in statistics. Basically, we will come to this expression in the next semester when we will ask something like whether some numerical variable depends on some qualitative characteristic of a person. Let's say we want to know are there different I don't know. Are there some differences in salaries between student graduates from economics department, from the energy departments, and from some other department like management department? So then we have one variable which is the education and the major of a person, and another variable is going to be the salary of a graduate. So that's how it works. So now let's conclude with the example of this and how this exactly works. So we have this joint density. We know that the expected value of x1 given x2 is this, and we know that the variance of x1 given x2 is, so now it must be x squared over 12. So we know the marginal density of x2, which is given here. It's just an integral of a joint density with respect to x1, and it's simply 1/2 x2. So we know this from lecture number 9. It's here. Yeah. So let's do this together just to understand the steps. So if you want to calculate the variance of x1, as it is given here, we need to calculate the following. We need to calculate the expectation of a variance of x1 given x2 plus variance of this expectation of x1 given x2. So that's our goal. So let's do this separately. Let's calculate the expectation of a variance first. And what do we know? We know that there is a conditional variance, which is x squared, x2 squared over 12, right? So it was a typo, which means that I need to integrate x2 squared over 12 over x2 dx2 and the values of x2 are bounded from 0 to 2 here. And this is the variance, and then I also need to multiply my variance by the density function of x2. So this is the marginal density of x2, which is given here, 1/2 x2. Because now I'm taking the expectation only for the values of x2, so that's why I'm using here the marginal density, and that's what we said here with respect to the distribution of x2. Right, so what do we have? We can take 1/24 out of the integration sign. X2 squared, sorry, it must be, this x must be here. So, and then I have an integral inside of x2 cubed, right? x2 cubed. So finally I have 1/24 multiplied by x to the power of 4 divided by 4, and here it's gonna be 2 to the power of 4 divided by 4, which is how much? It's 16 divided by 96, right? And when I divide this, 96 over 4, so it's 24. Must be divisible, right? So 96 over, yeah, 1/6, 1/6. So finally, the second part is what? The second part is that we need to calculate the variance of this expectation. And the variance of this expectation is what? We need to find this expectation squared first, the expectation of this expectation squared, and then we need to subtract the expectation of this expectation. Okay, so let me write down the expression to calculate this, and I think we will run out of time already. So how much is that? First of all, let's remember what is the expectation. It's x2 squared, so which means that I need to calculate this x2 squared over 4, so expected value squared, and its expectation, and minus this, minus the expectation of x2 divided by 2 squared. So this thing must be squared. Yeah, something like this. So this is the square, the expectation of a square. This is the square of the expectation. So finally, when you find this difference, you need to subtract from 1/6 this, and you will get the unconditional variance of x1. I think you will finish this on the exercise session. You will finish this calculation just to see that this variance must be equal to the unconditional variance. We can calculate, of course, unconditional variance in a simpler way. This is just, let's say, a connection between this conditional variance and unconditional variance. So, finally, I apologize that home assignment number 9 was not available. So particularly it's due to the outage of the web page during the weekend. So if you ever tried to access the course page on the weekend, you have seen that it has not been working, and I didn't have any chance to make a home assignment during the weekend. And basically in the working days, in the first part of the week, I don't have time for that. So tomorrow, these 2 home assignments are going to be available, and I will give you enough deadline to make them. So you will have 2 weeks in order to finish these 2 home assignments. Don't worry that you don't have time for them. You will have enough time. Joint distribution too. So after the exercise session on Saturday, there is gonna be also the home assignment number 11, and I guess my plan is to have one more home assignment number 12 after the next topic, and that's gonna be it, because we are heading towards the end of the course. So any questions to me about this material and these topics? Anything else?
No question. Thank you.
Okay, then let's have a break, and we will meet each other later for the microeconomics. Thanks for your attention.